Hi, in this video we're going to talk about quantifying uncertainty, and it's possible these words mean nothing to you right now, but hopefully by the end of the video they will be meaningful. So let's start with a recap of a few things that we've learned so far and then motivate this discussion about why might we be interested in quantifying the uncertainty around our estimates. We're going to look at data from a university called Elmhurst College, and we have data from a random sample of 50 students here. This is a university in the US, and we know their family income, so that's on the x-axis and in thousands of dollars. And we also know the gift aid amount that they received. And the gift aid is financial aid that does not need to be paid back. So this is not student loans, but it's basically scholarship that the students have received. And we're seeing a negative relationship between these two, which hopefully makes sense. If your family is wealthier or makes more money, then you are getting less gift from the university. Here's a linear model fit to these data, and we can see our linear model output, and we're going to focus specifically on our slope estimate. So that's negative 0.0431. So let's bring that up a little bit larger. So our slope estimate for family income is negative 0.0431. And what that number really means is that for each additional $1,000 of family income, that's a unit increase on the x-axis, we would expect students to receive a net difference of $43.10 negative. In other words, $43.10 less in gift aid on average, which is a really small number, but then again, our slope was a pretty small number. And so basically what it's saying is that $1,000 of family income difference, it's not a huge difference if you think about what the median income in the US is, for example, is associated with a reduction of $43.10 in gift aid. The question is it really exactly $43.10 for all students at this school? Or if we could imagine that this school is representative of all schools, which I'm not really sure necessarily that it is, but it might be representative of the type of school that it is. Could we say that that amount holds true for all students just based off of the 50 that we have data on? This is where the idea of inference comes into play. So what we mean by statistical inference is that it's the process of using sample data to make conclusions about the underlying population the sample came from. You might be thinking, why is there a picture of somebody cooking here? Let's imagine you're making some vegetable soup, okay? You chop up your veggies and you put it all in the pot, you pour some water over it, and then you start cooking. And at some point you ask yourself, did I salt this thing? Is it salty enough? What do? Do you drink the entire pot of soup, or do you actually just take a spoonful, taste it, and then based on the spoonful that you've taken, infer the salt level of the entire pot? We usually do the spoonful approach. And so that's basically what statistical inference is like. We take a sample and we taste that, and then based off of what we learned from that sample, our observed sample, we infer something about the population that we don't have data on. That's the entire pot of soup. And actually, to carry forward on this analogy, if you were to chop up your veggies, pour some water, and never mix anything, right? And then you were to taste just on top the water that's sitting on top, that's not really going to be representative of what your soup is going to ultimately look like. So usually what we do is we then stir the pot really well so that the sample that we're tasting is representative of the whole pot. And that is basically similar to the idea of random sampling. When we take samples, we want to take a random sample that's representative of the full population. We've given this analogy before earlier in the course, and we're coming back to it and now actually putting it in context of then what do we do next? If I have this representative sample, what can I learn from it about my population? So far we've done lots and lots of estimation. We calculated sample mean, sample median, sample slopes, and we used these data from samples to calculate sample statistics, which then can be used as estimates for population parameters. So I'm actually not that interested in just these 50 students from Elmhurst College. So for me, they are a sample that represents a bigger population, and I want to be able to make an inference about that full population. So here's a question. If you want to catch a fish, do you prefer a spear or a net? Unless you're an expert spear fisher, my guess is going to be a net, right? Because you're more likely to actually catch the fish with that than if you're actually fishing with a spear and you have to really hit that fish right on the head. Well, if you want to estimate a population parameter, do you prefer to report a range of values the parameter might be in, or a single value? This is similar to this fish and spear and net analogy. If we report a single point estimate, we probably won't hit the exact population parameter. So that 4310 or negative 4310 for our slope is probably not exactly our population parameter. If we report a range of plausible values, we have a good shot at capturing the parameter. So if I were to say negative 43.10 for the slope, give or take something, I'm going to have a better shot of capturing that parameter. Let's take a look at this example. Here is an example from the Gallup poll, a recent survey that they ran, or actually an ongoing survey that they've been running that they've recently published some results from. And the headline says, Britain's approval of US leadership at new low. So let's scroll down to see what they're talking about here. And so we're going to say Britain's view of US leadership quickly soured after President Donald Trump's election, with approval ratings plummeting to 26 percentage points between 2016 and 2017. The opinions have reached a new low point, however, during his fourth year in office. So it says that 15% of Britons approve of US leadership. So we can see this value over the years. And this is the 15% that they actually wrote this article about, because it is strikingly low, almost at an all-time low compared to all other years. So that's our estimate from the sample that Gallup managed to survey and get this number from. Whenever you read something like this, you want to scroll to the bottom of this. Usually it's at the bottom. Usually it's not right next to the estimate. And you'll see something like survey method. So let's go ahead and expand this and see, how did they get this data? How did they come up with this 15%? So it says these results are based on telephone interviews with approximately 1,000 adults age 15 and older, conducted in August and September of 2020 in the United Kingdom. For results based on the total sample of national adults, so that's that full sample, the margin of sampling error is 3.7 percentage points at the 95% confidence level. So what we mean by that margin of sampling error is that give or take. Remember, we said, wouldn't it be nice if I could report my sample statistic and then say give or take something to provide a range around it? Well, this is that range around the 15% sample statistic that Gallup is reporting. So they're really saying that the percentage of Britons who approve of US leadership is 15%, give or take 3.7 percentage points. This number is almost always reported. Sometimes it's not. And in that case, you really want to be suspicious about what that is, because if that number was much smaller or a lot bigger, that would be meaningful for the accuracy of and the precision of our estimates. So oftentimes you'll see this reported with survey results, and it's a really, really useful piece of information to really understand what we can estimate about our population. What we're going to talk about in this video is, how do they come up with this 3.7 number? How do we actually build this confidence interval around our sample statistic? So this range, this plausible range that we're talking about, is called a confidence interval in statistics. In order to construct a confidence interval, we need to quantify the variability of our sample statistic. So for example, if we want to construct a confidence interval for the population slope, we need to come up with a plausible range of values around our observed sample slope. So that negative 43.10 that I had, I need a plausible range around it. But what is it going to be? Plus or minus 10, plus or minus 20, plus or minus 3? That's what we need to decide. And this range will depend on how precise and accurate our sample mean is as an estimate of the population mean. Or in this case, our sample slope is as an estimate of the population slope. So whatever statistic you're thinking about, we're interested in its precision and its accuracy. Quantifying this requires a measurement of how much we would expect the sample population to vary from sample to sample. So here's a concept that is new that we haven't really talked about so far, and that can be a little bit kind of tricky to wrap your head around. So let's read that sentence one more time. We're talking about how do samples from the same population vary from each other? I'm going to give you two examples to try to solidify this a little bit. Suppose that in a different time, we were actually all sitting in a classroom, and then we split the class in half down the middle of the classroom and ask each student their heights. And then we calculate the mean height of students on each side of the classroom. So mean height of the students who are sitting on the left side and who are sitting on the right side. Would you expect these two means to be exactly equal, close but not equal, or wildly different? I'll give you a second to think about that. Hopefully you decided on close but not equal. We wouldn't necessarily expect two sample means to be exactly equal to each other to the decimal point, but we also don't necessarily expect them to be wildly different. Perhaps if we were talking about front of the classroom versus back of the classroom, we might anticipate a little bit more difference. Perhaps people who are shorter would prefer to sit closer to the front so they can see better. I'm not really sure if that's necessarily the case, but we could expect something. But left side or right side of the classroom, there's no reason why taller people will gravitate to one side and shorter people to the other. So we wouldn't expect these sample means to be wildly different either. So these are not two random samples from a population, but they are two samples from this population of a classroom. And we can see that their sample means are different and probably simply due to chance. Here's another example. Suppose you randomly sample 50 students and 5 of them are left-handed. If you were to take another random sample of 50 students, how many would you expect to be left-handed? If you're thinking something like 5, you're on the right track. Would you be surprised if only 3 of them were left-handed? Or would you be surprised if 40 of them were left-handed? I think if your original sample had 5 left-handed people out of 50, and then the next sample had 3, you might say, yeah, it's just random chance. Maybe the next one will have 7. But if 40 of the 50 you sampled were left-handed, you would probably think, do I really have a random sample here, or is there something else going on? So we expect sample statistics to vary from one sample to another. And how wildly they vary really depends on what we're measuring and our sample sizes and stuff. But in this case, we happen to know that being left-handed is not a super common outcome. I think the percentage I want to say is something like 10 to 13% in the population. So in that case, I think we would be, once we get a sample with 5 left-handed people, the next one with 3 might not surprise us, but the next one with 40 might. So that gives you something about how big we might expect the range for this plausible estimate to be. So how do we quantify this? We can quantify the variability of a sample statistic using a variety of methods. One of them is via simulation, and that's what we're going to stick with in this video. It's called bootstrapping, so we'll say a little bit more in a second about why it's called bootstrapping, but basically you need to be doing computer simulation to be able to calculate these bootstrap confidence intervals. And that lines up really well with everything that we've been doing so far in the class, and that's what we're going to stick with. It also has fewer assumptions in terms of probability distributions than the other approach, which is more theoretical based. So it's based on the central limit theorem, which is not just central to statistics, but it's about the central tendency of distribution of sample statistics. So it's called the central limit theorem, and you will most definitely learn about the central limit theorem in further detail if you were to take future stat courses. So here's that regression output again. And early on, when we first introduced regression in this course, we said we're going to focus on the estimate column, the intercept estimate and the slope estimate. And we said we're not going to say much about the standard error just yet. We're finally at the point where we are actually starting to talk about the variability majority of these estimates, which is called the standard error. But instead of working with the numbers that this output reports, which is calculated based on certain assumptions that rely on the central limit theorem, we're going to take a different approach. But to put things in context, that's what those numbers, the standard error numbers, are about. And then based off of those, we can also calculate confidence intervals or do what we call hypothesis testing, which is a different sort of statistical inference, where we would make some decisions based off of these p-value columns. So these are super important concepts as well, just not ones we're going to cover in this course. They will most definitely be covered in a future statistics course, where you're also learning a lot more about the theory underneath it as well. So back to bootstrapping. What do we mean by bootstrapping? If you've ever heard of the phrase pulling oneself up by one's bootstraps, which always makes me think of kind of stumbling over if I was to do that, it basically means accomplishing an impossible task without any outside help. And that's where the name bootstrapping comes from. The impossible task in this scenario is estimating a population parameter using data from only the given sample. We're calling this an impossible task, but that's basically what all of statistical inference is. So notion of saying something about a population parameter using only information from an observed sample is really the crux of statistical inference. So it's not so impossible. There are actually great ways of doing this, and bootstrapping happens to be one of those ways, and that's what we're talking about in this video. Here's our observed sample. So this is the same data you've seen before with that regression line that we fit in, and that's that slope negative 0.0431 that we've seen earlier. Here is data from our random sample of 50 students that we have observed. What I've done here is simulated, so this is not real. The gray points are not real, they're simulated, but I was assuming that, well, if you have these purple points, these are the observed students, chances are the rest of the population looks something like those gray points. So these have been generated assuming there are more students like the ones in the observed sample. And what we're really interested in is what would the slope be if we had the data from all the gray points for those points, because that would be our population parameter. So that would be our population slope. That's what we're after. We unfortunately don't have the gray data. I mean, I made it up, it's there, but it's simulated. I can't just then calculate it based off of this single simulation that I've generated. So I need a different method of doing that. What we're going to do is we're going to use this technique called bootstrapping to actually simulate samples and then use information from those samples to say something about our population parameter. And remember, our ultimate goal is to be able to report a range around that observed sample statistic, which was negative 0.0431. We just want to be able to find out how far out should I go. The way bootstrapping works is that we take a bootstrap sample, which basically is a random sample taken with replacement, super important, with replacement from the original sample of the same size as the original sample. So if I had these 50 students in a bag and I reached out and I randomly picked one out, recorded their family income and their gift aid, and then put them back in the bag, closed my eyes, shuffled, and randomly picked another one again, could be the same student or could be a different one this time, recorded that and did this 50 times to generate a new sample. That sample would have observations that were in my original sample as well. That's all that's in my bag. Those are the 50 students I get to work with. But that sample that I've now drawn with replacement from the original sample does not necessarily have to look exactly like the original sample because I'm drawing with replacement. So student 1 could appear twice or 3 times or something, while student 4 might appear never in this bootstrap sample that I've taken. And the idea with sampling with replacement is that, well, I don't get to those gray points that I've shown earlier. I don't get to have my population. So what I'm saying is, if whatever is in this bag, these 50 students, are representative of all the students in the population, I might just allow myself to pick some of them a few more times and some of them, fewer times, because in the actual population, other people like them exist as well. Then we calculate the bootstrap statistic. So that's whatever statistic you're after. We're after the slope, so that's what we would calculate for that one sample that I drew with replacement from the original sample. If we were doing a bootstrap interval for the mean, gift aid, or the proportion, or something like that, we would be calculating that. In this case, we're interested in the slope, so let's focus on the slope. I got my new sample, bootstrap sample of 50 observations. I'd fit another model to that, calculate the slope, put that in my pocket. And then I repeat it. I repeat steps 1 and 2 many, many times. Remember, we said we can't get away with a single simulation. We have to think about, what if I was to take more samples from the population? How different would they be from each other? Similar or wildly different, or somewhere in between? So we take another bootstrap sample, calculate another slope, put it in our pocket. Take another bootstrap sample, calculate a slope, put it in our pocket, and do this many, many, many times. And this is where computing comes into play. As you can imagine, we're not going to keep reaching into a bag and pulling things out. So we're going to simulate this using computing. And ultimately, in my pocket are going to be a bunch of slopes that I've calculated from these bootstrap samples. Then I take them all out of my pocket and I say, all right, let's see what you look like. Let's take a look at your distribution and see what are some slope values that we were likely to get when we tried this many, many times. So we calculate the bounds of our confidence interval, and we always associate a particular confidence level with it. 95% is one that's commonly used. So if I was calculating a 95% confidence interval, I would calculate that as the middle 95% of my bootstrap distribution. So hopefully this made a little bit of sense, but let's put that into practice a little bit. Here is sample number 1. Basically, I'm starting with my data frame, which was called Elmhurst, and then I'm taking a random sample of size 50, the same size as the original sample, with replacement. So I allow myself to capture certain values multiple times or certain values never from the original sample, and I save it. That's my bootstrap sample. I fit a model to it. This is what it looks like, and we can see that the slope is a little bit different. Now I get a slope of negative 0.0327. Then I take another one. Slightly different points, slightly different slope. Then I take another one. Slightly different set of points, slightly different slope. Then I take another one. Slightly different set of points, slightly different slope. We could keep going, but here's those 4 put together. So we can see that our lines are kind of moving around, and I've plotted these data kind of on top of each other. So you can see that we're not always necessarily seeing, so in this case, I should have 200 points on this plot, but we don't actually count 200 points because there's overplotting going on because certain students have been sampled for multiple samples. But the lines we can see are varying ever so slightly between sample to sample. We could keep going like this, but that's going to take a long time. So here is a picture based off of all 1,000 bootstrap samples. So 1,000, think large number, right? 1,000 or 10,000 are generally used values for doing bootstrap sampling. In fact, I think the recommendation is 15,000 for running them that many times. So here, those gray, like really, really thin lines that you're seeing are all the possible slopes I've gotten from all the various samples. The purple points are my observed data to begin with. So I haven't plotted all the bootstrap samples here as well. I've only plotted the regression lines that we've fit to those samples. So each one of those gray lines represents a regression model, and each one of them has a slope. So if you were to take out all of those slopes and make a histogram of them, this is what they look like. Where would you guess the center of this distribution is at? Somewhere around negative 0.04, just to the right of the negative 0.05. You're thinking the observed sample slope, which was negative 0.0431, you're right on the mark. That's our observed data. Everything is centered around our observed data, and we're assuming that observed data is a good representation of the population. But what we're saying is that around this observed slope of negative 0.0431, I can give or take a little bit. And this distribution tells me how much can I give or take? So if I actually wanted to get the middle 95% of this distribution, so there are 1,000 values plotted here, I basically chop off the 2.5% from either end, and I end up with a confidence bounds that are at negative 0.0695 on one side and negative 0.0219 on the other side. So those are the bounds of the middle 95% of my distribution. What do I do with those numbers? Let's go back to that interpretation of the slope we started the video with. We had said that for each additional $1,000 of family income, we would expect $43.10 less in gift aid. And then we questioned ourselves as to, do we really believe that number on its own for the full population? Well, now we can do something a little bit better. Instead of spearfishing, we can cast a net. We are 95% confident that for each additional $1,000 of family income, we would expect students to receive $69.50 to $21.90 less in gift aid on average. So instead of reporting the mid value, I'm basically reporting the range. And I am also stating my confidence level that goes along with that. If I was to change the confidence level a little bit, those bounds that I looked at on the histogram would move around, and hence the bounds of the interval would move around as well. So one thing we didn't do in this video was to go into too much depth of the code for generating these. The reason for that is that the code for generating these is just a little bit more than what we've seen so far. And my goal with this video is really to give you the notion that when we report estimates, we probably don't want to report them on their own, but we also want to quantify our uncertainty around them, just like the Gallup poll did with the margin of error, and we do that using confidence intervals. We introduced a simulation-based method for developing these confidence intervals, and conceptually went through that and graphically showed how those look. And finally, we're taking a look under the hood at the code that generated those results. So to do that, I am doing random sampling. So I'm going to start by setting a seed, and then I take Bootstrap samples 1,000 times. So that operation of pulling things out of the bag, making a sample of 50, and capturing that information of the sample of 50, that's what this function bootstraps from the tidy models packages do. We then create 1,000 separate samples, each of sample size 50. Now that we have these samples, what we can do is we can fit a model to them. So we have in a column our samples, and what we're going to do here is using the map function that we've seen before, but using it in a way that we haven't seen before inside a mutate to say, take these samples and fit a model to them and save the model output in a new column. And then from these model output, tidy them up and save the information in another column. So this is the reason why I didn't want to go into too much detail with the code, because the code is starting to get a little bit more advanced. So what I will say is that if this is the sort of thing you want to explore for your project, the code is here and we're very, very much happy to provide support. But if you're kind of following things along conceptually, that's perfectly fine too. Once we have our coefficients, we need to unnest them quickly, because for each model we have two coefficients, one for the slope and one for the intercept, and I'm only interested in the slope. And then finally what I can do is I can calculate the percentile interval for these coefficients, and the output of that basically looks like what we've seen in the previous slide, except we focused on the family income, the slope, and not the intercept, but there would be a similar interpretation for the intercept as well.